All right, everybody excited to take a look at some molecular representations? Good. All right, I am too. Anyhow, so we're going to learn how to communicate molecules, organic molecules. We're going to learn different ways to draw them this morning. So there's many ways to represent molecules, whether they be organic or inorganic. So we have Lewis structures. You all passed General Chemistry 1, so I know that whoever your instructor was, that they would have made you draw many Lewis structures over the course of the semester. You would have practiced drawing water and ammonia and simple molecules, right? And then we have a partially condensed structure. Now, what do you notice about the difference between the Lewis structure and the partially condensed structure? In the partially condensed structure, we omit carbon-hydrogen bonds. So those are left out. Then you have a condensed structure, which is very common in older textbooks, right? In old textbooks, before they had, sophisticated drawing software and computers like we do nowadays, they had to type everything out. And so condensed structures were widely used in old textbooks, but they're still important for us to understand. And that's where we omit all bonds, right? We just condense everything down, and we're going to get some practice on those this morning. And then the bond line structure, or the bond line drawing, as he calls it here, these would be, no joke, the industry standard, okay? The most important of all these structures would be the bond line structure, or the bond line drawing, and because that's what we're going to use the most in this class. And something that you notice, because this molecule, it's the same molecule that's being represented in all four of these structures. This is isopropanol, so isopropanol, which is rubbing alcohol. So this is isopropanol, this is, and this is. So they're all isopropanol. But what you notice about the bond line structure, if you took the time to watch my video about functional groups, and if you read chapter 2, you notice that in the bond line structure, your eye trains in on the functional group immediately, right? Immediately it focuses in on that and brings your attention to it. And so we have some other Lewis structures down here at the bottom, but what do you notice about these three compounds? The three compounds at the bottom, the isopropanol, the N-propanol, and the ethyl methyl ether, they're all what? They're all constitutional isomers of each other, aren't they, right? Which is just a little bit more practice on that. All right, so let's see if we can draw a Lewis structure for each of the compounds that are shown here. And so you notice on the first one, okay, if I just use my highlighter here, this carbon I'll highlight in yellow, and we'll do this one in green, and maybe I'll do this one in red, and then blue, just to kind of keep track of things like that. So you notice that the carbon in yellow has two hydrogens bound to it, but it's also next to a carbon, okay? So that suggests that it has how many bonds? It has two single bonds and one double bond, right, in order for it to be neutral. So we're going to start with that carbon, so it's going to have two single bonds, I should say, to the two hydrogens, but it's going to have a double bond to the carbon in green. So this would be the green carbon, this would be the yellow carbon. Now that carbon in green has one hydrogen attached to it, then it has an oxygen. Do you remember oxygen from our first chapter? The oxygen is what we call divalent, right? Oxygen always has two bonds and two lone pairs. And so in this case, it's going to have two single bonds and two lone pairs. Then we're going to go to the carbon in red, okay? Then that carbon in red has two bonds to two hydrogens, and then it's also bound to the carbon in blue, all right? And so the carbon in blue has a hydrogen attached to it, but those parentheses tell you that there's how many CH3 groups attached to that carbon? Anybody? 2, right? Because there's a subscript 2 on the end of that. Exactly. See, you guys put it all together very quickly. So we'll put there's a CH3 here, there's a CH3 here, and there's a hydrogen here. So we'll fill in the 3 hydrogens on each of these, and there you have it. We have our Lewis structure. And so you should be able to look at a condensed structure and be able to interpret that as a bond line structure, as a Lewis structure, what have you. So if we take a look at the next one, I'm going to start over on the right-hand side of this one. I'll highlight this carbon in yellow. We'll do this one in green, and we'll do this one in red, okay? So something like that. So we're going to start with the CH2 group that I have the yellow highlighter on, and that is attached to an oxygen. Remember, oxygen is divalent. It has two bonds and two lone pairs. So it's attached to the hydrogen on the end, right? It also has two hydrogens on it, and then it's attached to the carbon in green, and then that one is going to be attached to the carbon in red. Exactly. Thanks, you guys. Okay, so we'll go a little faster. All right. Everybody seems to be picking up on this with relative ease. So then we have 2 carbons here, right? And then we have 2 more carbons here. Not the prettiest drawing ever, but it will have to suffice. Okay, so we have these 2 groups on the end. And if you're sitting there going, why isn't he using words like methyl and ethyl? It's because we haven't gotten to that yet, but we will soon enough. We're going to get into nomenclature sooner, so I'll start using words like methyl, ethyl, propyl, terbutyl, all that kind of stuff. Okay, but for now, we'll just call them CH3s and CH2s, okay? Technically, a CH3 is a methyl, a CH2 is a methylene, and a CH is a methine. But anyhow, I'll put that down on the screen later on, so don't stress about that right now. So going back to our idea of bond line structures, and this is just a rehash of what we looked at last week, okay? So again, if you're given a Lewis structure or a condensed structure, you should be able to draw a bond line structure from that. So sp2 and sp3 hybridized carbon atoms in a straight chain should be drawn in the zigzag format. Just one more time I'll tell you, just remember, if you wanted to draw the bond line structure of this molecule here, which is butane, okay, if you wanted to draw the bond line structure of that, remember, when your pen or pencil touches the paper, what is that? That's the first carbon, right? So you can see, you know, if you're, and every once in a while, somebody in class will raise their hand, and it's a perfectly legitimate question. They'll say, well, this one, they went up for 1, 2, 3, 4, right? Would it be okay if I did 1, 2, 3, 4? Would that be okay? What's the answer? Absolutely, right? They both represent the exact same molecule. It doesn't matter whether you zig or you zag first, okay? Either one, they both communicate the same thing. It's one of the best things about science, right? A science class has nothing to do with my opinions. If it's right, it's right. You know, if it's wrong, it's wrong. But if it's right, it's right. I can't argue with the structure. That's correct. Other things that you'll start to pick up on as you practice drawing your bond line structures day after day after day is that if you have an sp2 hybridized carbon, as you see here in this molecule, this is acetone, which is found in paint removers and nail polish remover. So I like to throw a name out there once in a while, right? Acetone. In the organic chemistry lab, sometimes we use it for washing glassware. But so if we draw our double bond and our 2 single bonds to this carbon here, we're going to want those bonds to be as far apart as possible, right? And so we try to impart a bond angle of 120 degrees. Right, you see the one that's bad here? It even looks kind of goofy when you look at it. I'm sure you've all picked up on that by now, okay? If somebody wrote that as a structure on the first quiz or something, I'd be like, okay, I see you're communicating effectively. I understand what you're drawing. But eventually you learn how to draw structures and you impart the proper bond angles. Rule 3, when drawing single bonds, the direction in which the bonds are drawn is irrelevant. Now, I didn't bring my model kit with me this morning, but I think that all of you probably have enough experience with molecular model kits by now that you know that there's free rotation around a single bond, isn't there? There isn't free rotation around a double or a triple bond, but there's free rotation around a single bond. And so you could rotate this bond, you could rotate this bond. And so the 2 structures that you see here at the bottom are identical, right? They both have a chain of 5 carbons in a row with 1 carbon coming off as a substituent in the middle, okay? So that would be called what? 3-methylpentane would be the name of that compound. A trick that you can use sometimes when we get into nomenclature later on is if you're looking at 2 compounds and you're wondering if they're tough ones and you're saying, are these the same compound or not? I'm not sure. What you can do is just name them. If you name the 2 compounds and you get the same name, well, they must be identical. If you get different names, then they're not identical. Anyhow, let's move on from there. So all heteroatoms, atoms other than carbon and hydrogen. So when I say a heteroatom in organic chemistry, all I'm talking about is any element on the periodic table that's not carbon or hydrogen. So what are the most common heteroatoms that we're going to see in this class? Well, oxygen, nitrogen, sulfur, phosphorus, a little bit the halogens. I'll just put X for a halogen, meaning chlorine, fluorine, bromine, and iodine. But those don't have hydrogens attached to them anyway. But anyhow, the heteroatoms, we always draw them explicitly. There's no, bond line way of leaving them out or something, okay? So we always include those atoms, and we always draw the hydrogens that are attached to them, okay? So we don't leave those out. So you can see that the Lewis structure here, we have this hydroxyl group here, and we make sure we include it in the bond line structure with the hydrogen attached to it explicitly, right? We have to draw that out. And you can see that these two bond line structures, they're both correct, but in one of them, he includes the lone pairs on the oxygen, and on the other one, he leaves them out. Now, both are correct, okay? There's nothing wrong with this structure here. However, what are we doing in the second week of class? We're learning the material, right? You're trying to learn it, right? I'm trying to convey it to you the best I can. And so if I can make a recommendation for at least your first semester of organic chemistry, don't leave lone pairs out. Just put them in. And sometimes the textbook leaves them out deliberately. When you're doing your practice problem, just put them in. It only takes a second, right? Put them in, and it will make things move along a little bit more smoothly. Another rule, the cardinal rule, never draw more than 4 bonds to a carbon atom. Okay, we have a name for that. We call that the Texas carbon. Okay, if you draw, that's exceeding the octet rule. Okay, and so that's a bad thing. Okay, if somebody draws 5 bonds to a carbon, it's not good. We used to have a joke in the industry. We'd say if somebody comes in for a job interview and we ask them a question, they draw 5 bonds to a carbon, we're like, thanks for coming out. It was nice meeting you. Have a nice drive home kind of thing. Anyhow, so don't draw 5 bonds to a carbon. All right. So let's get into some 3-dimensional drawings. And it says here that all molecules take up space in 3 dimensions, but it's difficult to represent a 3D molecule on a 2D piece of paper, on a blackboard, or your notebook, or a screen, right? So we have to find ways to convey a 3-dimensional structure in 2 dimensions when we're writing. And so what we do is we use dashes and wedges. And I'm sure all of you have seen dashes and wedges when you practice drawing your Lewis structures in General Chemistry 1. You learned the tetrahedron, right? You would have learned trigonal pyramidal, and we even discussed those in Chapter 1. And so we use dashed lines to show bonds that are going away from us or back into the page, and we use wedges to show bonds that are coming out of the page, okay? And so this one here, this would be a dash, and then this one here, this would be a wedge, okay? It's coming straight for us, right? Anyhow, if you look at that structure on the far right, it's kind of interesting, isn't it, right? You've got a 6-membered ring, right? So you've got a 6-membered ring like this, but then you have a bridge, right? There's like a bridge that goes between this carbon and this carbon, right? So it's showing you that it comes up and then goes down like this. So it's like you've got a 5-membered ring and a 6-membered ring fused together. And so if you're struggling with it, you're like, I'm not sure what that would look like. Something that you might want to do is get a molecular model kit and build that model so you can see the bridge in this bicyclic structure. All right, does anybody recognize this kind of compound here? No? Anyhow, we'll worry about that later. All right, so let's keep moving. So Fisher projections. So if you have studied sugars at all, and I know that some of you have taken biology classes, maybe some type of biochemistry class, where you would have learned about glycolysis or the Krebs cycle, right? So you know a little bit about glucose, okay? So you know that glucose is a carbohydrate. Carbohydrates, we call them sugars, right? There's many different types of sugars, xylose, lysose, whatever, allose, maltose, okay? But anyhow, the person who characterized the sugars, the family of aldoses and hexoses and aldohexoses and ketohexoses, anyhow, I'm kind of just mumbling here. But anyhow, the person who characterized all the sugars originally was a guy by the name of Emil Fischer. And the thing is that initially when Fischer was drawing out the structure of sugars, they have all these, hydroxyl groups on them, okay? Is he was kind of drawing them like this, but then he gets sick and tired of drawing all the dashes and wedges. And so he developed the Fischer projection as a shortcut sort of for imparting, it's just a way to substitute all those dashes and wedges. Then we have a Haworth projection, which we use for rings. So we use it for cyclic compounds only. And you can see here that it's showing you the ring is kind of tilted like this towards you. You see the OH group is pointing up, the bromine is pointing down. Then we have a chair conformation, and later on, we're going to get some practice in drawing chairs. And then we have a bicyclic compound here. So if you're like, why is the 3-dimensional structure of a molecule so important? It's because the receptors on the cells in your body are three-dimensional as well, right? And so the shape of a compound is going to govern how it interacts biologically. And so it's important that we understand the three-dimensional structure of a molecule, and so we have to be able to represent that on paper. All right, let's see if we can draw some bond line structures from some condensed structures. And I'm just going to take a guess here that this wouldn't take any of you very much time to do. So if we take a look at this carbon here, this is the same compound we started out with, isn't it? I don't know, maybe not. But anyhow, we have this carbon here, which is attached to 2 hydrogens and 1 carbon. That means that it must be sp2 hybridized, right? It must have a double bond between the 2 carbons that I have highlighted. And so we would have something that looks like this, a double bond, right? This would be this carbon, and this would be this carbon here. Then we have an oxygen after that, and oxygen, as you know, is divalent, so we can put in the 2 lone pairs. And then we have a CH2 group. Then we have a CH. So this CH2 group is going to be this carbon here. This CH, or methine, is going to be this guy here, and then it's going to have 2 CH3 groups coming off of it like this, okay? Let me give you a second to see if you can draw the next one. So just take a break here and see if you can draw the next 2, actually. I'll give you a second, and I'll come around and take a quick gander to see what Kai did. Yeah, it looks perfect. Yeah. All right. Everybody going for it here. So remember, to me, the tools of mastering anything in organic chemistry, pretty much anything, would be a pencil and paper. Okay, I like pencils. Why? Because I make a lot of mistakes when I'm trying, right? So don't be afraid to make a mistake. Okay, never be afraid to just jot something down and say, oh, that's not right. Let me try that again. Okay, never be shy to do that in organic chemistry. So if we take a look at this guy here, okay, if you take a look at this carbon that I have highlighted in blue, it has an OH group attached to it, but then it has 3 CH2, CH3 groups attached to it, right? So if we want to draw the bond line structure, I'll start with the bond to the OH like this. Okay, so this carbon that I have highlighted in blue is the carbon I have highlighted in blue. All right, so attached to that, I've got 3, right? Are you with me on that? You guys pointed that out to me very quickly the first time. There's 3 of these groups, right? So all I have to do is say CH2, CH3, CH2, CH3, CH2, CH3, done. Okay? Are you with me on that one? So that would be what? Triethyl methanol or something like that. Anyhow, name's not important. Okay, if I look at the next one, what do you notice about this carbon here? It has 1 bond to this carbon that I have highlighted in yellow, but then it has 2 CH2, CH3 groups attached to it. So that means what must its hybridization be? sp2, right? It's got a double bond between the carbon in red and the carbon in yellow. Does that make sense to everybody, right? So we could just start with that double bond. I think that's the best place to start. So I'll put my yellow highlighter on this one, my red highlighter on this one. And so on the red carbon, I've got 2 CH2, CH3 groups, okay? So 1 and 2. Now, if you drew yours a little bit differently than me, there's nothing wrong with it, okay? Let's say in this structure, you had, an ethyl group going like this or something, or this ethyl group was, I don't know, over here like that. It's the same thing, okay? It doesn't matter. There's free rotation around a single bond. So don't get stressed like, oh my goodness, my structure doesn't look exactly the same as his. It doesn't matter, okay? We try to draw it as cleanly as we can, okay? But, sometimes we have to make a little room there, and somebody's might look a little bit different than somebody else's, okay? All right, good with me on that one? All right. If you're sitting there and you're like, I didn't get it right the first time, what should you do? Panic? No, run out into the parking lot and start screaming at people. No, you go home, you give it a shot, right? You give it a try, okay? And then, shoot me an email if you can't figure something out. So let's move on to functional groups. Now, there's only so much kind of preaching at you or lecturing that I can do when it comes to functional groups. Who saw my video about functional groups? Who saw that awesome song about functional groups? Alkanes, they're driving me insane, which is kind of a silly place to start the song because an alkane isn't a functional group, but I see where the guy's going, okay? It's just good music, right? Anyhow, so that video, the one that I made was pretty long, and then the other one, I think, it's kind of funny, but it will help you remember things, something silly like that. So functional groups, let's get into functional groups. And I'll go over this kind of quickly because you're going to have to spend some time alone with the functional groups in order to get to know them. So bond line structures, as I told you earlier on, what's another thing that makes bond line structures, besides being fast to draw, is that it's easier to see bonds being made or broken during a chemical reaction. So if we take a look at the reaction that's drawn here using condensed structures, you can see what's going on. You guys obviously notice, you say, yeah, there's a double bond here and there's no double bond in the product, okay? But if you look at the bond line structure, it's just cleaner. It just is, okay? Again, you see the double bond and you see the double bond goes away. This reaction that you see here with the H2, hydrogen gas, and the platinum, that's called a hydrogenation reaction. And that's something that we're going to discuss in detail in chapter 8. But anyhow, the bond line structures make it more obvious to see functional group transformations taking place. And so what I have highlighted in yellow, that double bond, is a type of functional group. Did anybody pick up which type of functional group that is? Don't be shy. It's an alkene. Exactly. Good. You guys have been studying. Absolutely. You're all 100% correct on that. So what's neat is that when certain atoms are bonded together in specific arrangements, they undergo specific chemical reactions. Put in other words, once you learn about the functional groups, okay, once you learn how an alcohol reacts, how an alkene reacts, how an alkyne reacts, how a carboxylic acid reacts, once you learn that, you are able to look at a molecule, maybe a drug, and say, it's going to react this way, okay, inside of the human body. Or if I put it in acid, it's going to do this, right? The stomach is an acidic environment, right? If it's in a basic environment like the intestine, this might happen, right? Does that make sense to you, okay? So this is what a medicinal chemist does. The person looks at functional groups and is sometimes able to predict reactivity of the molecule. So the characteristic groups that we call functional groups, which is where atoms are bonded in a specific way, everybody has to learn them, okay? So you have to learn them, I had to learn them, the people that will come after you, and the people who came before you. We all have to learn our functional groups. Now, I admit the functional groups take a bit of memorizing, okay? But you must memorize the functional group. So let's go over them kind of quickly. The first one is an alkyl halide, and you remember the halogens, fluorine, chlorine, bromine, and iodine. You notice that in your textbook, they only point out chlorine, bromine, and iodine. You're like, what about the fluorine? Well, fluorine is an important element in organic chemistry, but it doesn't come up almost never in this class. It might come up in the acids basis chapter a little bit, but in terms of reactivity, we don't really look at fluorine a whole lot. So an alkyl halide, as you all pointed out to me just 2 minutes ago, if I have a double bond between two carbons, what do I call that again? An alkene. And when I have a triple bond, it's an alkyne, right? So it takes alkynes to make a world. All right. Next, if we have an OH group, that's an alcohol. Right, we saw earlier with the morphine molecule that it had two OH groups, and so you'd say morphine has two alcohol functional groups in it, right? You could look at the structure of cholesterol, which I'm sure many of you have, right? You took a biology class, you studied the phospholipid bilayer, and you said, oh, well, in there's cholesterol molecules in there, right? It ends with it's an alcohol, right? There's an OH group in cholesterol. Okay, let's keep going. A couple of minutes ago, you heard me mention acetone, which you guys would know is found in nail polish remover and paint thinners. This is acetone here, acetone. It turns out acetone is the simplest possible ketone you can have. And so if you have a carbon with a double bond to oxygen, and that carbon, this carbon here, is flanked by two R groups, we call that a ketone. Okay, so a ketone. Just give me 1 second. So one thing that you're going to notice shows up in a bunch of functional groups, like an aldehyde, carboxylic acid, acyl halide, ester, amide, okay, acid anhydride. They all have this in them. They all have a carbon with a double bond to oxygen like this. If you see a carbon with just a double bond to oxygen, so obviously that carbon does not have a complete octet, so we're just taking it as a piece. We call that a moiety in organic chemistry sometimes. So if we're just talking about this moiety, this part of a functional group here, we call this a carbonyl, okay? A carbonyl. So that means a ketone has a carbonyl, an aldehyde, you see, has a carbonyl, a carboxylic acid has a carbonyl, right? Esters have carbonyls, acid halides, and so on and so forth, okay? So when you see that carbon with a double bond to oxygen, that's a carbonyl group, okay? So when you have a carbonyl flanked by two R groups, that's what we call a ketone. Now, if you're looking at R and saying, I've been looking at the periodic table for the last 60 seconds. I'm not finding any element R. There is no such thing as element R, is there? Does there anybody pick up what does R stand for? Could anybody tell me? It stands for remainder, right? But it is just a carbon chain, right? It's some kind of carbon-based group. Now, it's not on this table here, but it's down here, right, Kai? It says the R refers to the remainder of the compound, which is, as Brianna was saying, it's usually some kind of carbon chain. Okay, it could also be aromatic, which we're going to look at in a second, but either one is totally fine. Okay, so let's go back to the carbonyl. If the carbonyl is flanked by two carbon-based groups, two R groups, it's a ketone. If it's flanked by one R group and one hydrogen, it's an aldehyde, right? And you guys would know the simplest possible aldehyde is what? Formaldehyde. Yeah, exactly, right? Which you guys know is used as a preservative. So this is formaldehyde, okay? Then we have a carboxylic acid. So a carboxylic acid has a carbonyl. It has an OH group on one side, a hydroxyl, and then it has an R group on the other side. Now, a trap that students will fall into sometimes, and I can totally see why, is they might say, well, it's two functional groups. You got an alcohol and then you have a ketone. No. When you're looking at functional groups, you have to take what? The 30,000-foot view. An organic chemist, meaning you and me, we always have to step back and look at the entire molecule before we start making judgment calls. So we look at everything and we say, that's not an alcohol and a carbonyl. That's actually a carboxylic acid, right? I look at the entirety. Next, if we have a carbonyl that has an R group and a halogen, like chlorine or bromine, that's what we call an acyl halide. Sometimes you'll hear me. I don't call them that. Sometimes I call them an acid halide, okay? But either one is fine. All right, let's keep going. Next one. If you have an oxygen that's flanked by two R groups, we call that an ether, okay? And the ether that's shown here is diethyl ether. You probably noticed that the sulfur analog of an alcohol, right? OH was called an alcohol. If we have SH, it's called a thiol, okay? There's a common name for thiols. Sometimes they're called mercaptans, okay? We're not going to use that a whole lot. I'll bring it up in organic chemistry too with you. How about that? Then you might notice that the sulfur analog of an ether, right? If you replace the oxygen of an ether with a sulfur, it's not called a ether, it's called, right? It's called the sulfide, okay? And I'm sure you've all heard the word sulfide before, right? They're smelly compounds. Then you have aromatics. Who remembers the aromatic from general chemistry? Yeah, I'm sure you would have heard about aromatics a few times in general chemistry. And so if you had me as an instructor, I might have explained, about Auguste Kekulé and how they knew the structure C6H6, but they didn't know They knew the molecular formula, C6H6, but they didn't know the structure, and he discovered it. So anyhow, anhydrides aren't going to show up a ton in this class. You see they're only mentioned in chapter 20. So that would be organic chemistry too. However, if you're in the lab with Dr. Lakakula or Mr. Geiger, they might ask you about infrared spectroscopy of anhydrides because they're kind of interesting. Anyhow, then we have an ester. Okay, so an ester is where you have a carbonyl, and then you have an R group on one side, oxygen with an R group attached, right? So if this was a hydrogen, that would be what functional group? Carboxylic acid, exactly. But if you replace that hydrogen with an R group, it's an ester. Esters are kind of interesting compounds because if you like the smell of things that have fruity smells, like bananas and cherries and strawberries, right? I probably told you guys before that that's the result of esters. Then we have amides. If you've studied proteins and peptides, maybe a little bit in a biology class, what we call a peptide bond is nothing more than an amide bond. So what's an amide? It's when we have a carbonyl. On one side, we have our R group, or carbon-based group, and on the other side, we have a nitrogen. And the last one is the amine. Okay, so an amine is just when we have a nitrogen. The simplest amine, and again, you know I don't like to use the word simple, but the simplest amine would be NH3. What's the common name of NH3 again? Ammonia. Exactly, ammonia. Okay, so an ammonia is an amine, but if we start replacing those hydrogens with carbon-based groups, then it becomes an amine, okay? Now, the numbers that you see on the far right of all of these, those are the chapters which they're going to be discussed in. However, in this class, the class you're enrolled in, Chemistry 3101, the other section, Dr. Anderson's section and my section, we both want our students to memorize the functional groups right away because, as you saw, we're going to be tackling infrared spectroscopy in week 5, okay? And so we're going to be using functional groups constantly in that chapter. That's what we're going to be doing over and over and over, okay? And so if I can encourage you, one thing Mr. Dion likes to try to do, I like to try to motivate my students. There's only so much I can do, but if I can encourage you, look, think about this, you guys. All the time that you put in memorizing the functional groups, not 1 second of it will be lost, okay? Let me ask you guys a question. Do you think the functional groups are going to change next semester? No. Do you think they're going to change a year from now? Do you think they're going to change 50 years from now? They won't, okay? When I'm gone from this planet, it'll still be the same old functional groups being taught here on Earth, okay? And so if you memorize those functional groups, they'll always be good, right? It's always going to be important. As long as organic chemistry is a part of your life, the functional groups, every second you put into it, it's going to be time well spent, okay? I don't like to make promises, but I can promise you that, okay? All right, let's take a look at these two. What would these be? Cardiovascular drugs, I guess. Altenolol and enalapril are drugs used in the treatment of heart disease. They both lower blood pressure. They have different mechanisms of action, but they reduce the risk of heart attack. So, using the table, could we identify some functional groups? Let's just kind of go here. So, don't one person answer them all. I'm sure some people have them all mastered, but we'll just kind of go around. Can anybody, we'll start with the atenolol. Can anybody throw one out at me? Don't be shy.
Amine.
Sorry?
Amine.
An amine? Yes, there's a beautiful, you're starting right on the left. So you're like, I'll start with the left, right? And we'll just go across, all right? So we have an amine. What's the next, or what's another one? Sorry? Carboxylic acid. So there's no carboxylic acid in atenolol, but in the enalapril, right, there's a carboxylic acid over here. Absolutely. So we'll put here carboxylic acid. What about the atenolol? Let's see if we can, go ahead.
There's an amide.
There's an amide. Yes, absolutely. So you can call it an amide. You can call it, people from England, like they have British, accents, sometimes they call it an amide, right? Or some people call it, I worked with a guy who called it an amide, okay? As long as you give it the proper name, that's fine by me, right? Potato, okay? What else we got in there? Sorry, what did you say this guy here? Go ahead.
Ether.
An ether, yes. There's a beautiful ether in there, isn't there, right? Anyhow, so there's an ether. Kai, what were you saying?
There's an alcohol.
Alcohol, yes. There you go. A nice alcohol here. And we'll do this one in unison. We'll just like we're in church, okay? Everybody holler it out. What is that's the aromatic, absolutely. See, you guys got it. You don't need any help from me. Aromatic. All right, so Kevin identified the carboxylic acid and enalapril. Any other functional group? Go ahead.
Is that an amide that's part of the
Part-
member ring?
Yep, absolutely. This is an amide right here. Yep. There you go. So we got amide here. All right, what else we got?
You have an amine right next to it.
Yeah, there's an amine here. Sure, absolutely. I saw a hand in the back. Naomi, was that you or? Go ahead.
I was going to say the amine.
Yeah, what else you got though? Give me, what about this one? Could you identify this one here? That's an ester, right? It's a nice ester there, yeah? Good, an ester. And everybody knows this one, right? Yeah, thanks you guys. Again, never be shy to holler out an answer in my class. Okay, good. Aromatic, what do you think? Not too bad? All right, so you can imagine on quiz 2, I kind of finished it up yesterday. I have a question where I put a molecule and I just say circle and identify some functional groups, right? You guys are going to just circle them, label them, and it's all good. So identifying lone pairs, and again, like I told you, I don't like to make promises to people, right? Because promises is risky, right? But I can almost promise you that if you practice your organic chemistry, eventually, Catherine, putting in the lone pairs, you won't be thinking about it, okay? You're going to, right? Once you do it enough, there's only so many bonding patterns that we look at in this class, right? We're really only talking about 4 or 5 elements 95% of the time, so it starts to get repetitive, okay? So eventually you're going to pick up on, how many lone pairs do I put in this oxygen? Well, if this oxygen has a negative charge on it, and it's got drawn only with one single bond. Now you can see the answers here on the right, but you do the math in your head. You say, well, oxygen has 6 valence electrons. It's got 1 stick. 6 minus 1 minus something gives me -1. Well, that something is 6, right? So that means it's missing 1, 2, 3 lone pairs of electrons. Does that resonate with everybody, right? And so there's going to be times, in fact, there'll be a question on your quiz where I give you a structure with no lone pairs, and I say, put in the lone pairs, right? I ask you guys to put in the dots, okay? And so that's what you're going to do. And so when it comes to oxygen, right, when we're talking about oxygen, that's what this whole slide is about, okay? What are the bonding patterns for oxygen? Well, as we saw in the previous slide, when oxygen has 1 bond and 3 lone pairs, it has a -1 charge. When it has 2 bonds and 2 lone pairs, it has a neutral, or it's neutral. It has a charge of 0, right? And then if it has 3 bonds and 1 lone pair, it has a charge of +1, right? Now you're like, that one's not a mystery to me, right? Because I remember in chemistry 1411, I must have drawn hydronium, I don't know, maybe 1 billion times, right? I know you guys were getting sick of ammonium and hydronium, right? Making you draw ice tables, but you start to remember these things after a while. So besides carbon, hydrogen, oxygen, what's the 4th most common element we're going to see in this class? Nitrogen, right? We're going to see a lot of nitrogen. You saw nitrogens and amines and amides, okay? And so what are the bonding patterns for our friend nitrogen? So when nitrogen has 2 bonds and 2 lone pairs, has a -1 charge, right? Just do the math. Nitrogen has 5 valence electrons. If it has 2 bonds, okay, how many lone pairs must it have? Or how many, right? It must have 4 unpaired electrons or 2 lone pairs, right? In order for it to have a -1 charge. Does that make sense to everybody? Right? So going back to molecules like ammonia, when nitrogen has 3 bonds and 1 lone pair, it's neutral. And then when it has 4 bonds and no lone pairs, it has a charge of +1. And as I just mentioned, I'm using the same old yarns over and over here. But again, Catherine, do you remember writing this molecule down, or this ion? Ammonium, did you write that down a bunch of times when you were doing your ice tables? You're like, holy heck, that buffers chapter, it just never went away, right? Everything was hydroxide this, hydronium this, water, ammonia. Who remembers that from chemistry 1411, equilibria? Yeah, okay. If you're wondering, do I never have to think about that again? The answer is no. You do have to think about that again. Equilibria is going to come up a lot in the acids bases chapter, and it's going to come up in subsequent chapters as well. Okay, so bonding patterns. So now what we'll do, we don't have time to answer all of these, but if we just kind of go over them, just the first few. If we start with A, this would be called N-methylmorpholine would be the name of that compound. But anyhow, the nitrogen has no charge on it, right? It's neutral. If it had a charge, they'd have to tell you, okay? It's not implied. They'd have to show you that. So how many lone pairs are missing from that nitrogen? One lone pair. Thank you. I'll use a different color. I'll use blue, okay? What about on the oxygen? 2 lone pairs. See, you guys are faster at this than me. What about the oxygen with a positive charge in B? 1 lone pair is missing from there, right? 3 bonds, 1 lone pair, positive charge. Okay, what about, I'll ask you guys about C. What functional group is in C? Heck yeah, awesome, nice. Okay, we'll start with this oxygen on the top. How many lone pairs are missing on it? 2 lone pairs, yeah. So 1, 2. And what about this oxygen down here? And remember, there's no trick questions in organic chemistry. Go ahead. 2, yeah, absolutely, right? There you go. Oops, that's not very pretty, is it? There we go. 1, 2, okay? If we look at this guy, you can see this oxygen is neutral. So 2 bonds, 2 lone pairs. The oxygen with a positive charge, 3 bonds, 1 lone pair, right? The nitrogen with a negative charge. When nitrogen has a negative charge, it has 2 bonds and how many lone pairs? See? Now, if you're like, oh, you said I wouldn't have to think about it. I'm thinking about it. Well, yeah, you probably are right now. Once you've done it 100 times, it'll be like negative charge, 2 bonds, 2 lone pairs on my nitrogen, right? Eventually, if you practice, you're going to get very used to it, and you'll get very good at it, okay? All right, so I'll let you finish the rest on your own time, okay? You remember you have the answers in the solutions manual. Has anybody looked at the solutions manual yet? Show of hands, who's looked at the solutions manual? Is that thing great or what? Okay, I shouldn't call it a thing. Is that solutions manual wonderful or what? Jackson, did you look at it at all?
I don't have it.
Okay, you got to get it. You got to get it. Everybody, if you don't have the solutions manual, get the solutions manual. It will really help you, okay? It helps you a lot. Go ahead.
Actually, I don't know if any of the rest of you had this issue. I sent you an email about this, but I tried to get a copy of the solutions manual, and buying it on Wiley's website, it was like showing zeros for the price and not actually letting me do it.
I have that issue too, and I don't remember how I solved it, but I was able to figure it out.
Yeah, you should be.
Weird.
Yeah.
Because when you go to buy it, it like logs you out automatically and you relog in, but when you relog in, it zeroes it out as if there's nothing in your shopping
Right,
cart.
and then you should be able to open it up.
Put it in your shopping cart.
Yeah.
Okay.
Yeah.
I have the same issue.
Yeah. All right. So we're agreed. We can access the solutions manual. All right. Well, let's keep moving. So let's talk about carbon atoms with formal charges. Okay. So we've gone over oxygen being neutral or +1 or -1. We've gone over nitrogen being neutral or +1 or -1. Now let's talk about carbon being neutral when it has 4 bonds, of course, when it's positive and when it's negative. So we're going to see a lot of carbons with positive charges. We call those carbocations. Okay, so a carbocation. So a carbocation is a carbon that has 3 bonds. Okay, 3 bonds and no lone pairs. So if you look at all 3 of those carbons that are highlighted in green here, you have to put the positive charge on there, right? But we're using bond line structures, and in a bond line structure, we omit carbon-hydrogen bonds, right? We don't put those in. And so it's implied how many bonds there are to hydrogen. For one example, if we just zoom in on this guy here, we see that we have a positive charge on this carbon, but there's only 1 bond drawn explicitly to that carbon there. Therefore, it's implied that there's how many hydrogens? 2, right? As you see on the screen, right? So again, you can't just say, oh, that carbon must have a positive charge, right? It has to be drawn explicitly. Furthermore, if you have a carbanion, in that case, your carbon is going to have 3 bonds and 1 lone pair, right? Just do the math. If you take this carbon with our negative charge, our carbanion, carbon has 4 valence electrons, -3 sticks, -2 dots, gives you, -1. And so a carbanion and a carbocation. Now, if we go back to the carbocation, who could tell me what the hybridization of a carbocation always is? It's sp2, right? Because you have 3 hybrid orbitals to make the 3 bonds, but then you have an unhybridized p orbital with no lone pair in it, okay? That's the one that has the positive charge, right? But if you have a carbanion, on the other hand, what's the hybridization of a carbanion? It's not sp2, it's sp3, right? You have the 3 bonds, okay, that are the 3 sigma bonds made from the sp3 hybrid orbitals, and the lone pair is also in an sp3 hybrid orbital. And so you should understand that since a carbocation and a carbanion have different hybridizations, they have different molecular geometries, don't they? The carbocation is going to be trigonal planar. Trigonal planar. I'm kind of running out of space here. And a carbanion is going to be trigonal pyramidal. Exactly. Trigonal pyramidal. Okay? There you go. So you guys just explained to me, or gave me a little lesson on kind of what's covered on the bottom of this slide. So again, you have to understand when you have a carbocation that the carbon with the positive charge is trigonal planar, so it's flat. Okay, you can see the plane here between those 3 bonds, the dash, the wedge, and the single bond, the bond drawn in the plane, excuse me. And then we have trigonal pyramidal for our carbanion. All right, and this is going to be super important for you and me later on when we get into mechanisms where we see carbanions being formed and carbocations being formed. All right, the molecular geometry, I mean. All right, so let's start talking about resonance, okay? And resonance is one of those topics that I'm sure you all read the textbook before coming to class. You're like, yes, Mr. Dion, as long as you have no follow-up questions, yes, I did, okay? All right, anyhow, when it comes to resonance, I'll admit that it's one of those things that sometimes you just have to sit down and close your eyes and think about it a little bit. Like, what is going on here, you know? Sometimes I'll be laying on the sofa at home and my children have a line, which is, Daddy, are you sleeping or meditating, right? Because sometimes I'll read a book and I'll just put it on my chest and just lay there and have to think about it for a few minutes before I understand what's going on. And I'm sure you can relate to that too. You're like walking around thinking about having some kind of scientific thought and you're like, now I understand. You know, it takes a little bit of time, okay? So resonance might take you a minute to figure it out, but I'll do my best to explain it to you the best I can. So when we draw our beautiful bond line structures, which are really nice, okay? They're all wonderful and everything, but remember, we're trying to represent atoms and molecules with just, pencil and paper, okay? It's not the easiest thing in the world to do. And so sometimes a single drawing does not adequately describe a chemical species. And so in that kind of case, we have to draw what are called resonance structures. Now this anion that I have here, this is the acetate ion, okay? Acetate. You guys remember acetic acid and its conjugate base, the acetate ion? You're like, do I? Okay. Well, if you look at acetate, you see that you have this one bond line structure here where the negative charge is on this oxygen. And if you're thinking all you did was flip them, no, I'm going to tell you, this is still this oxygen. And now we show the negative charge on the green oxygen like this, okay? And so this arrow that you see here, this is a resonance arrow, okay? It's not an equilibrium arrow. An equilibrium arrow looks like this. This one is used for equilibrium. So don't mix up the two. They are two different things. If I ask you to draw a resonance structure, don't draw an equilibrium arrow. And if I ask you about equilibria, don't start drawing resonance arrows, okay? They're two different things, okay? So what the resonance structure is showing us, or what those two structures are showing you, is that the negative charge that's shown in the ion is not localized, meaning it's not just on one of the oxygens. It's actually spread out. It's delocalized across both oxygen atoms, okay? And so we're going to get some practice in drawing resonance structures. And so we say that these two structures contribute to the resonance hybrid, okay? Now drawing a hybrid, it can be difficult with an organic molecule. And so what we do is we draw the individual resonance structures and we say it's not that the molecule or the ion is vibrating back and forth between the two. It's not that at 1 second it's this and the next second is this. Remember, there's limitations to our drawings. What we're saying is if you take both of those structures into account, The actual structure of the acetate ion is a hybrid of the two, right? It's a blend of the two. And the analogy that's used in your textbook is that, what is this delicious fruit that you see here? That's a nectarine. Nectarines aren't natural. I mean, they were created by humans, okay? Humans invented the nectarine, okay? And where does a nectarine come from? It's a cross between a plum and a peach, okay? So people crossed a plum tree and a peach tree, and they developed the nectarine. But when you look at a nectarine, it's not like 1 second it's a peach and next second it's a plum, right? It's always a nectarine. Does that make sense? Okay? Another example would be a mule, right? Where do we get a mule? It's a cross between what? A donkey and a horse, right? They take a monocot and a dicot, right? They cross it and they make a seedless fruit, right? Because the mule can't reproduce. But you look at a mule, it's not like 1 second it's a donkey. You come in the next morning, it's a horse, sweet, Anyhow, no, it's a mule, right? Anyhow, so there you go. So now what we're going to do, go ahead.
Why is it valuable to picture those as two separate species rather than just seeing them as the same molecule but rotated within 3D space?
You're going to see that as we move along. Okay, we'll kind of flesh that out. Okay, there's a long answer, and we're going to go through that in these next few slides. All right. So before we can get into drawing some resonance structures, we have to cover the topic of curved arrows. And throughout organic chemistry, we're going to be using curved arrows to show the movement of electrons. So when you see a curved arrow drawn like the one that's shown on here, you'll notice, if you're very observant, that the head of the arrow has two lines on it, right? Like this. That means it's showing the movement of two electrons, okay? There's another type of curved arrow which has only one barb on the end of like this. That shows the movement of one electron. This will be discussed in chapter 10. So do not worry about the movement of one electron. Every curved arrow that we're going to be drawing for the next many chapters until April, okay, are going to involve the movement of two electrons always. Why? Because there's two electrons in a bond. So it says here, and these are the words of David Klein, the sooner you master this skill, the easier this course will be. So what do you have to do? It starts with P, ends with practice. Anybody? Practice, exactly. So the arrow is going to start where the electrons are located. It might be a lone pair. It might be a bond. And the arrow ends where the electrons will end up after the electron movement. And so it says here, we're going to explore curved arrows to show other reactions in chapter 3. So in chapter 3, we're actually going to, so listen to me very carefully. In chapter 3, we will discuss reactions, okay? We're going to use curved arrows to represent acid-base reactions. In chapter 2, we're not looking at any reactions. We're only using the curved arrows to represent what? Resonance structures, okay? That's the name of the game for today. So don't worry about reactions yet. We're not there. So in order for you to be able to employ, to engage, to be able to utilize curved arrows, you have to learn a few rules. Right? Have you guys noticed that? I mean, you've studied science for long enough at this point. What is science? What is a science degree? Well, it's a lot of things, right? But a lot of it is learning the rules and then learning how to employ those rules, right? Or showing somebody that I know the rules, let me show you how to use the rules, okay? So here are the rules for drawing curved arrows. Let's take a break. Break's over. So what are the rules? Rule number 1, never show a single bond, which is a sigma bond. Never show a sigma bond as being delocalized. Now remember, what are we talking about today? Are we talking about reactions? No, we're only talking about resonance. When we get into reactions, oh yeah, we'll show single bonds breaking, but we're not there, okay? We're just talking about resonance. So when we're dealing with resonance structures, we never show a single or sigma bond as being delocalized. So obviously, this is not a resonance arrow, what you have shown here, because you broke a bond. Where did the bond go, right? So that's not resonance, okay? So don't break any single bonds in resonance, okay? Single bonds break in what? Chemical reactions, not resonance. All right. So, and this is something that I would say, if you ask students this at the end of the class, they'll lose sight of it sometimes, okay? So try not, and I realize there's a lot to remember in this class, okay? I don't want you to leave this class and be like, Mr. Dion had unrealistic expectations. I'm human too, okay? So if you forget a couple of things here and there, it's normal. But try to remember this if you can, is that resonance occurs for electrons existing in overlapping p orbitals, pi bonds, and lone pairs. So the name of the game when you're talking about resonance is that your lone pairs, it's electrons that are in overlapping p orbitals. So where do we get electrons in p orbitals? They either have to be in a pi bond, right? Because how do you make a pi bond? It's the overlap of two p orbitals. Or it has to be a lone pair that's in an unhybridized p orbital, right? And again, I'm not trying to talk bad about my students or whatever, okay? But every once in a while, we'll be in the 10th week of class and I'll say, what kind of orbital is this lone pair of electrons in if it's participating in resonance? And I get just crickets, So remember, if it's participating in resonance, it's in what kind of orbital? A p orbital, okay? So just try to remember that as we move through. And I admit you won't be thinking about that when you're drawing your structures. You're just trying to get through it, right, at the beginning. But just try and remember that. So next one is, do we want to break the octet rule, you guys? Do we like breaking the octet rule? Of course not, okay? Are there exceptions to the octet rule? Sure, you learned them in General Chemistry 1, right? But do you see exceptions to the octet rule for carbon, nitrogen, oxygen, and fluorine? No, okay? So we don't break the octet rule. So these arrows, I always love this slide. I love the bad arrow. It's like wagging your finger, like bad arrow, right, honey? Bad arrow. How could you do that? And I don't even like to draw the result of these because as your instructor, I get kind of queasy when I draw something on the screen that's not correct because somebody might just wake up and be like, is that what you're supposed to do? No, okay? But I'll do it once, okay? So if you take a look at this bad arrow, right, if I was to draw the resonance form here, there's my resonance arrow. So you'd have your 3 bonds to hydrogen, but then you've got a double bond here like this. Is there such thing? I'll ask you guys a funny question. What do we call this carbon? The Texas carbon, right? In my slides with the Texas flag with the carbon on it. Actually, you had to search Google Images for that, okay? And this is the first time I've ever put it in my slides. But anyhow, so no, that's a huge violation, okay? So if you draw the other ones, and you don't have to. I mean, this is America. You could get arrested for this kind of stuff. So, you don't want to draw those arrows, right? Because then you're exceeding the octet rule, okay? So do we break the octet rule for the most ubiquitous atoms in this class? No, we're not going to do that, okay? And I know you guys wouldn't do it anyway, okay? The next one, and this is one that, again, this is why you come to class, is to learn this kind of stuff. Second row elements, carbon, nitrogen, oxygen, fluorine, will sometimes have less than an octet. That's okay. But they're never going to have more than an octet. Can we have a carbocation? Sure, there's nothing wrong with a carbocation. But a positively charged carbon, does it have a complete octet? No. This carbon here, the carbocation, it's surrounded by how many total electrons? Can anybody tell me that? How many electrons are there in a bond? 2. How many bonds are attached to that carbon? 3. So it's surrounded by how many electrons? 6. That's not an octet, is it? Right? It's not surrounded by an octet, but that's okay. It's okay to have a carbocation. We just can't exceed the octet rule. Okay, cool. So in each of the following cases, bad arrow. So we're going to look to see if there's any violations being done here in any of these resonance arrows. So we'll just see if they're breaking any rules. So if you look at the one that's in the top left-hand corner, I'll just throw it out to you guys. You guys see any violations in here in this one? It breaks the octet rule, doesn't it? Okay? If you were to draw another bond to that nitrogen, it would have 5 bonds, and that breaks the octet rule. So I'll just put, I'm not going to write bad arrow. I'm just going to put exceeds octet. Okay? Exceeds octet. Octet. So maybe I'll put an X over it or something like that. What about the one next to it? And I'll circle them just so you make sure you know exactly which one. Is that okay? Yeah, I'd say it's okay. You'd get a carbocation and you'd get an oxygen with a negative charge, but that would be okay. You're not breaking the octet rule. And you're like, hold on, the oxygen has a negative charge. Yes, but if an oxygen has a negative charge, it's, okay, just because something has a negative charge doesn't mean it's exceeding the octet rule, does it? Right? This oxygen that I just drew is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. That's an octet. That's cool, okay? So there's nothing wrong with this next one. So I'll just put next to it a big old, that one's okay. What about this one here? Is that a good arrow, bad arrow? Heidi, what do you say? Bad arrow, right? It's like you're smiling. You're like, who drew that? You know, what kind of person would draw something like that, right? That's breaking a single bond. That's not a resonance structure, is it? Right? So we'll scribble down there. Breaking, breaks single bond, single bond. This one here, what would you say about that one? That one's okay. Yeah, I'd say that one is okay. Oh, just for an aside, this kind of functional group, if you have a carbon with a triple bond to nitrogen, it's funny that it's not included in the list of functional groups. Does anybody know the name of this functional group? No? Okay. So this one, you should know it. It's called a nitrile. Okay, this is called a nitrile. If you're like the nitrile gloves, yeah, like nitrile gloves. Okay, so a nitrile. The reason I bring that up is, again, in chapter 14, the infrared spectroscopy, we'll look at nitriles, and then with Mr. Geiger and Dr. Lakakula, you'll take a look at nitriles as well in that class a little bit. Okay, so that one's all right. What about the one next to it? I'd say this one is also okay. And what about the last one? Is that one okay or not okay? It's trickier. Why are you saying not okay? I agree with you.
It's gonna exceed the.
It's going to exceed the octet rule. But why do students find that one tricky? It's because the bond to the hydrogen isn't drawn explicitly in a bond line structure, so you might forget about it. Okay? But that carbon already has 4 bonds. So that's going to be a bad arrow, right? It's going to exceed the octet rule, okay? So we'll just put here exceeds octet. All right, so we'll put a crisscross over that one. There we go, not too bad. All right, so drawing resonance structures, or draw the resonance structure of the following compound, or drawing the resonance structure of the following compound requires one curved arrow. The head of this curved arrow is placed on the head of the curved arrow is placed on the oxygen atom, and the tail of the curved arrow can only be placed in one location without violating the rules. Draw this curved arrow. Let me give you a second to see if you can draw the curved arrow. And I'm going to draw the result of it. I'll draw the resonance form, but it's just asking you to draw the curved arrow. And it's telling you that the head of the arrow has to end up on the oxygen. So where would the tail of that arrow start? All right. Where would the tail of that arrow start? So could anybody tell me where it would start? Could you just go ahead? Yeah, it starts on the pi bond, doesn't it? Right? So it's going to start here, like that. There you go. Does the curved arrow have to touch the pi bond exactly like this? No, it doesn't have to touch it. It can if it wants to, okay? Just make sure it's clear. Don't try to, make it halfway in between, and he'll never know what I'm trying to do here. Well, if I don't know, then I can't grade it correct, okay? So if we draw the result of that, what's it going to look like? So we're still going to have our bond to oxygen, but now the oxygen has how many lone pairs? 2 lone pairs. So where the heck did our positive charge go? Positive charge heaven? No, where did it go? Go ahead.
The carbon to the left.
Yeah, exactly. You're right. It went on this carbon, didn't it? Right? Because that carbon has no hydrogen attached to it. Now it's got 3 bonds. So if you start with something that's positive +1 overall, right, the result of your resonance arrows have to give you something that's +1 in the end. If you start with something neutral, it has to be neutral. If you start with something negative, it has to be negative. Go ahead.
Is it possible to kind of keep going with this though, since it sort of flips and they're identical?
Not this one. No, there's no way to do it with this one. All right, we will see some examples where you can draw multiple resonance structures. So now what we're going to do in section 2.9 is we're just going to take 2 concepts that we've covered already and put them together in a sandwich to make a new section. That's all we're doing. So we learned about formal charges. We've learned about resonance structures. So let's just put the 2 together. So it says here, when using curved arrows to derive resonance structures, sometimes you start with something that's neutral and you end up with some formal charges. But remember, if you're starting with this structure here, which is neutral, those curved arrows, whatever is the question mark, whatever that answer is, it has to be neutral, doesn't it? Are you with me on that? So you must indicate the formal charge in order to draw a valid resonance structure. So they gave you the starting material. They gave you the 2 curved arrows. Could you draw the result of those 2 curved arrows? Okay, could you draw the result? Well, I think some of you have tried this one already, so I'll just kind of go through it here. But if we just draw at first what hasn't moved, we'll start with the things that have, with what hasn't moved, okay? This is what hasn't moved, because we see that this lone pair right? The tail of the arrow starts on a lone pair, but the head ends right smack dab in the middle between the oxygen and the carbon. Therefore, that indicates that you're making a pi bond. Are you with me on that? And then the tail of the other arrow starts on the pi bond. It's not explicitly touching it, but it's implied, since pi bonds are weaker than sigma bonds, that the pi bond is breaking. How many electrons are in a pi bond? 2. And the head of the arrow is ending up on this carbon. And so what's going to end up on that carbon in the resultant resonance structure? There's going to be a lone pair. So we started it with something that's neutral. Is there a formal charge on this oxygen? Yes or no? Yes, there's a charge of +1, isn't there? So there's no way you can go from neutral to +1. That must mean that there's a -1 somewhere, isn't there? Where is it? It's on this carbon, isn't it? Right? Because that carbon has a hydrogen attached to it, right? So it's implied that it's there. You see why mastering bond line structures is so important. You have to get really used to looking at the structure and saying, it looks like there's 2 bonds in one lone pair, doesn't it? But you know that there's actually 3 bonds in one lone pair. Give me a thumbs up if that makes some sense to you, okay? All right, groovy. Let's keep going. So, in each of the cases below, what we should start with is penciling in some lone pairs, then draw the curved arrows required to convert the first resonance structure into the second resonance structure. So, if I pencil in the lone pairs, okay, we'll pencil them all in. That's not the most pretty lone pair, is it? There we go, there we go, there we go, and there we go. Okay, so all of our lone pairs are penciled in on all 4 of these. So now, can we draw the curved arrows that take us from here to here? What are the curved arrows going to look like? Well, let me ask you this. Am I breaking that pi bond? Obviously, because it's not in the resultant structure. Where did those 2 electrons go? Electron paradise? No, they made a new pi bond, didn't they, right? So I put them between the carbon and the 2 carbons, the carbonyl carbon and the other carbon, okay? And now, if I was to just draw that arrow and just stop right there, threw my pencil down and said, I'm done. Is that a good curved arrow the way I've drawn it? No, because I'm breaking the octet rule, aren't I, right? So what do I have to do? I have to break this pi bond and put the lone pair up here like this. Does that resonate with everybody? See what it's the proper use of the word resonate, right? Anyhow, so what I want you to do before class on Friday, okay, is I want you to, at a minimum, read the remainder of the molecular representations chapter, because we're going to tackle drawing multiple resonance structures, okay? So if you can, I would read the chapter and I would try as many practice problems as I can. Don't say, and again, I'm not pointing a finger at anybody here because I know you guys wouldn't do this, but you know, sometimes first year students will do this